Hello, and welcome back to Dr. Logic Awkwardly Does Logic. We're going to talk some more about the possible axioms that we can add to System T to generate new, stronger systems of logic that have modal reduction principles. So I'm going to start right away bringing up our whiteboard so that I can just remind you of what these principles are that we talked about at the end of the video last time. So the first one is that possibly P implies necessarily possibly P. The second, possibly necessary P implies necessary P. The third, possibly P implies possibly P. And the fourth, necessary P implies necessary P. So the question we want to answer is what happens if we add each one of these to system T? What kind of systems do we get? What kinds of modal reduction principles follow? Now, the first thing to note is that all of these are converses of theorems of T. So anytime that we add one of them, we will then get a modal reduction principle. However, we don't have to go through and add each one of them individually because some of them are equivalent to each other. In fact, I will show you that if I have 4, so suppose that it is given, perhaps because it's an axiom, that necessary P implies necessary P. From that, I can prove very easily number 3. So if necessary P implies necessary P, then contraposition says that not necessary P implies not necessary P. We can then use modal interchange to shove the negations through to convert all of the modal operators. So this follows that possibly not P implies possibly not P. But then we can just do uniform substitution, replace each of these P's with a not P, and then we'll have some extra negations. We'll just do double negation at the same time to get us possibly P implies possibly P. Now, each of these steps was an equivalence, which means that I could also start at 4 and run the proof entirely backwards and get to number 1. So, well, we can get to the first step of the proof, which is number 4. This was confusing. Anyway, the point is, if I go this direction through the proof, I get from here to here. So this means 3 and 4 are equivalent, and we don't actually have to look at them individually. We can just look at one of them. The same is going to be true of 1 and 2. So suppose that we have as an axiom, possibly P implies necessary possibly P. Well, contraposition allows us to conclude that if it's not necessarily possibly P, then it's not possible that P. I bet you know what's coming next. Modal interchange. We change all of our modal operators, shove the negation all the way through to the atom. How you see why standard form is so useful? And then we can do the same uniform substitution trick, replacing P with not P, and then doing some double negation so that we get possibly necessary P implies necessary P. So that shows that from this formula, from formula 1, we can derive formula 2. And again, we can run the proof entirely opposite, and then we get this. So now instead of having 4 formulas we need to look at, we've only got 2 pairs. We only need to worry about what happens if we take one of these and add it to our system. In fact, now I'm just going to erase these proofs because we're going to need the space. If you take number 1, you don't need to add either 3 or 4 because you can derive number 4 from number 1. So that is what we are going to do next. Let me get my cursor swapped back over. Come on, I want to draw. So let's take number 1. Possibly P implies necessarily possibly P. Let's take this as our new axiom, and then what we're going to do is we're going to prove this. Now, first thing to recall is that this is system T that we are adding this axiom to. So we have both the T axiom, necessary P implies P, and the theorem T1 that P implies possibly P. So we're going to take a couple of substitution instances of that. First, a substitution of the axiom where we replace the P with possibly P. So necessarily possibly P implies possibly P. This is uniform substitution where we've substituted possibly P in for P into the T axiom. Propositional logic then says, look, this is just, you've got an inference from A to B and an inference from B to A. So we can put these together and have an equivalence between necessarily possibly P and possibly P. So propositional logic, stitching 1 and 2 together. Now I'm going to take a substitution instance of T1. So I'm going to substitute in necessary P for P in this guy. So this says necessary P implies possibly necessary P. Now, we've got this lovely equivalence that we've just proven in line 3. I'm going to do another substitution instance on this. So this is, again, substituting in necessarily P for P on line 3. So this gets us necessarily, possibly, necessarily P, if and only if, possibly, necessarily P. Read what I write, not what I say. Now, this is again an equivalence, but we can always break equivalences down into the two implications involved. So if we do that, we've got possibly necessary P, taking this side, implies necessarily, possibly, necessarily P. So we are going the implication from here to here. But the fact that we have various equivalences means that we can also reduce things. So note number 3, exactly the same trick that we did essentially to show the equivalences of these two formulas and these two formulas, we can do to get another version of 3. Uniform substitution, putting in not P for P, doing some modal interchange. I will leave the details to you as an exercise, but if we have 3, we also have that necessary P is equivalent to possibly necessary P. So I'm just going to note this as an exercise. It's derivable from line 3. If you want to try to give your proof of how to get line 7 from line 3 in the comments, I'm happy to take a look and check your work. But just note that I am skipping over some steps in order to get the equivalence that I need. There we go. So this means that anytime that we have diamond box, we can reduce it to just box. Well, look, we have a diamond box right there. So I'm going to do substitution of equivalence using this new equivalence in line 7 on line 6 to get that possibly necessary P implies necessary P. So I've dropped that diamond. But now, if you take a look at what we have here at line 4, this says, if necessarily P, then possibly necessary P. Line 8 says, if possibly necessary P, then necessary P. Stick lines 4 and 8 together with transitivity, and you have that necessarily P implies necessarily P, which means that if you start from this one, which is what we have right here, you can prove this one. So 1 is equivalent to 2, 3 is equivalent to 4, and if you have 1, you can prove 4. Now, the other doesn't hold. I will show you this in another video, but just remember this for now. But this means that we've got 2 things that we can look at. We can add this to system T and get, so we can add T plus necessarily P implies necessarily P, and that will get us one system. And then T plus possibly P implies necessarily possibly P will get us another stronger system, because from this system, you will be able to prove this one. Now, this is a whole bunch of proofs and bits and bobs and equivalences and implications and everything, but this provides us with the motivation for the next two systems that we are going to look at. They're going to be system 4 and system 5. And in the next video, I will say a little bit about where did systems 1 to 3 go. So join me next time, and until then, take care. Cheers.